Welcome back to Learning as a Hobby, everybody. In this video, I'm going to start on the differential equations book that I'm going to be using for my studies here. Um, and the book that I'm going to be using, which I just got in the mail a couple days ago, is this one, Differential Equations with Applications and Historical Notes, third edition by George Simmons. This book is a classic in the field of differential equations, so I'm excited to make my way through it. Especially, I love books, math books that have give you a sense of the history of the subject along with while they're teaching you the math. So I'm psyched to go through this book. It's quite a thick boy if you look at it. I already went through chapter 1, section 1. So we'll do the notes for that today in this video. And I'm going to post right after I finish this video. I'm going to post the solutions to some of the exercises that I did. So let me start by just reading out like I usually do. I'll start by reading the preface to the book by the author, Mr. Simmons. He has a preface for each of the editions, but like I did with Spivak, I think I'll just read the preface to the first edition because that's usually where the author, explains what his pedagogical ideas are behind writing the text. So there are some differences between the editions, mainly in that the later editions have some extra material that the first edition didn't contain. Particularly, there's a chapter on um, numerical methods for solving differential equations that was written by a different author. Let me see if I can see who the author for that chapter is. By John Robertson. So the last chapter in the book, chapter 14, is on numerical methods, and that's written by John Robertson rather than the author of the rest of the book, George Simmons. So let me read George Simmons's preface so we can see why he wrote the book, what he wanted to accomplish with it and everything. And then I'll move on to my lectures for the notes that I took down on chapter 1, part 1. All right, so here's the preface. To be worthy of serious attention, a new textbook on an old subject should embody a definite and reasonable point of view, which is not represented by books already in print. Such a point of view inevitably reflects the experience, taste, and biases of the author, and should therefore be clearly stated at the beginning so that those who disagree can seek nourishment elsewhere. The structure and content of this book express my personal opinions in a variety of ways as follows. The place of differential equations in mathematics. Analysis has been the dominant branch of math for 300 years, and differential equations are the heart of analysis. The subject is the natural goal of elementary calculus and the most important part of mathematics for understanding the physical sciences. Also, in the deeper questions it generates, it is the source of most of the ideas and theories which constitute higher analysis. Power series, Fourier series, the gamma function, and other special functions, integral equations, existence theorems, the need for rigorous justification of many analytic processes. All these themes arise in our work in the most natural context. And at a later stage, they provide the principal motivation behind complex analysis, the theory of Fourier series, and more general orthogonal expansions, Lebesgue integration, metric spaces, and Hilbert spaces, and a host of other beautiful topics in modern mathematics. I would argue, for example, that one of the main ideas of complex analysis is the liberation of power series from the confining environment of the real number system. And this motive is most clearly felt by those who have tried to use real power series to solve differential equations. In botany, it is obvious that no one can fully appreciate the blossoms of flowering plants without a reasonable understanding of the roots, stems, and leaves which nourish and support them. The same principle is true in mathematics, but is often neglected or forgotten. Fads are as common in mathematics as in any other human activity, and it is always difficult to separate the enduring from the ephemeral in the achievements of one's own time. At present, there's a strong current of abstraction flowing through our graduate schools of mathematics. This current has scoured away many of the individual features of the landscape and replaced them with the smooth, rounded boulders of general theories. When taken in moderation, these general theories are both useful and satisfying. But one unfortunate effect of their predominance is that if if a student doesn't learn a little while, I'm sorry, one of the unfortunate effects of their predominance is that if a student doesn't learn a little while he is an undergraduate about such colorful and worthwhile topics as the wave equation, Gauss's hypergeometric function, the gamma function, and the basic problems of the calculus of variations, among other ideas, then he is unlikely to do so later. The natural place for an informal acquaintance with such ideas is is a leisurely introductory course on differential equations. Some of our current books on this subject remind me of a sightseeing bus whose driver is so obsessed with speeding along to meet a schedule that his passengers have little or no opportunity to enjoy the scenery. Let us be late occasionally and take greater pleasure in the journey. That aligns with my goals for this whole video series. So already I'm on board with this book. Okay, applications. It is a truism that nothing is permanent except change, and the primary purpose of differential equations is to serve as a tool for the study of change in the physical world. A general book on the subject without a reasonable account of its scientific applications would therefore be as futile and pointless as a treatise on eggs that did not mention their reproductive purpose. This book is constructed so that each chapter, except the last, has at least one major quote unquote payoff, and often several, in the form of a classical scientific problem, which the methods of that chapter render accessible. These applications include, excuse me, the brachistochrone problem, the Einstein formula E equals mc squared, Newton's law of gravitation, the wave equation for the vibrating string, the harmonic oscillator in quantum mechanics, potential theory, the wave equation for the vibrating membrane, the prey-predator equations, nonlinear mechanics, Hamilton's principle, Abel's mechanical problem. I consider the mathematical treatment of these problems to be among the chief glories of Western civilization, and I hope the reader will agree. The problem of mathematical rigor. On the heights of pure mathematics, any argument that purports to be a proof must be capable of withstanding the severest criticisms of skeptical experts. This is one of the rules of the game, and if you wish to play, you must abide by the rules. But this is not the only game in town. There are some parts of mathematics, perhaps number theory and abstract algebra, in which high standards of rigorous proofs may be appropriate at all levels. But in elementary differential equations, a narrow insistence on doctrinaire exactitude tends to squeeze the juice out of the subject, so that only the dry husk remains. My main purpose in this book is to help the student grasp the nature and significance of differential equations, and to this end, I much prefer being occasionally imprecise but understandable to being completely accurate but incomprehensible. I'm not at all interested in building a logically impeccable mathematical structure in which definitions, theorems, and rigorous proofs are welded together into a formidable barrier which the reader is challenged to penetrate. In spite of these disclaimers, I do attempt a fairly rigorous discussion from time to time, notably in Chapter 13 and Appendices A in Chapters 5, 6, and 7, and B in Chapter 11. I'm not saying that the rest of the book is non-rigorous, but only that it leans toward the activist school of mathematics, whose primary aim is to develop methods for solving scientific problems, in contrast to the contemplative school, which analyzes and organizes the ideas and tools generated by the activists. Some will think that a mathematical argument is either sorry, some will think that a mathematical argument either is a proof or is not a proof. In the context of elementary analysis, I agree, and believe instead that the proper role of a proof is to carry reasonable conviction to one's intended audience. It seems to me that mathematical rigor is like clothing. In its style, it ought to suit the occasion, and it diminishes comfort and restricts freedom of movement if it is either too loose or too tight. History and biography. There's an old Armenian saying, "He who lacks a sense of the past is condemned to live in the narrow darkness of his own generation." Mathematics without history is mathematics stripped of its greatness, for like the other arts, and mathematics is one of the supreme arts of civilization, it derives its grandeur from the fact of being a human creation. In an age increasingly dominated by mass culture and bureaucratic impersonality, I take great pleasure in knowing that the vital ideas of mathematics were not printed out by a computer or voted through by committee, but instead were created by the solitary labor and individual genius of a few remarkable men. The many biographical notes in this book reflect my desire to convey something of the achievements and personal qualities of these astonishing human beings. Most of the longer notes are placed in the appendices, but each is linked, but each is linked directly to a specific contribution discussed in the text. These notes have as their subjects all but a few of the greatest mathematicians of the past 3 centuries: Fermat, Newton, the Bernoullis, Euler, Lagrange, Laplace, Fourier, Gauss, Abel, Poisson, Dirichlet, Hamilton, Liouville, Chebyshev, Hermite, Riemann, Minkowski, and Poincaré. As T.S. Eliot wrote in one of his essays, someone said, "The dead writers are remote from us because we know so much more than they did." Precisely, and they are that which we know. History and biography are very complex, and I am painfully aware that scarcely anything in my notes is actually quite as simple as it may appear. I must also apologize for the many excessively brief allusions to mathematical ideas most student readers have not yet encountered. But with the aid of a good library, sufficiently interested students should be able to unravel most of them for themselves. At the very least, such efforts may help to impart a feeling for the immense diversity of classical mathematics, an aspect of the subject that is almost invisible in the average undergraduate curriculum. George F. Simmons. Okay, so that's the preface, and you can get an idea of what George Simmons thinks about the subject of differential equations. And one of the reasons I chose this book was because I agreed so much with the ideas that he had in his preface, as well as his choice of topics that he goes over in this book. And like I said, I like the historical notes. There are many textbooks I like that, along, like I said a few minutes ago, along with the development of the subject, they give you a sense of where it came from, right? What its history is, so you can see the natural development of where these ideas come from. I think it's really useful in wrapping your head around something. So that's the book I'm going to be using for the ODEs part of my of my project here. Um, I'm gonna go over the notes I took down in section 1.1. Actually, I think it's 1.1, 1.2. Let me just double check. Yeah, so I have my notes that I'm going to show you in a minute were for 1.1 and section 1.2. And then have I did a bunch of the exercises for those 2 sections. And I'll show you, like I always do, I'll show you the solutions to those in a separate video. So let me go through my notes now. I'll bring up where's my XP pen? I'll bring up my notes that I already wrote out. Okay, all right. Hopefully that shows up. So like I said, chapter 1.1 and 1.2. So section 1.1 is just basically on some definitions, things that you need to know, explaining like what a differential equation is, etc. So we start with that definition: an equation involving one dependent variable and its derivatives with respect to one or more independent variables is called a differential equation. That's the definition. I should also say, like in my other videos, this is just my summary of what I read. So I'm, just sort of um, uh, bringing out just like the main idea. So it's like a skeleton of the chapter. You should read it yourself though, because he's a really good writer, actually, George Simmons. I enjoyed reading these 2 sections so far. So That's the definition of a differential equation. That's what we're going to be studying. Right, we have two types of well, there's two types of differential equations we're going to be looking at, and then we have the definition of what it means for the order of a differential equation. But in this book, mainly we're going to be looking at ordinary differential equations. An ordinary differential equation is one in which there's only one independent variable. So in other words, you'll be able to um, graph these solutions in the Cartesian plane, the XY plane. Okay. The order of the differential equation is the order of the highest derivative present. So we'll see some examples of differential equations in a second, but that's what the order means. So, and generally, the higher the order of the differential equation, the more difficult it is to solve in a general sense. Not, it's not always the case, but um, the other type of differential equation, which I'm going to use a whole other book for partial differential equations, which we'll do in a separate, series of later on after I finish this first, semester. A partial differential equation is one involving more than one independent variable, so that the derivatives occurring in it are partial derivatives. Okay, so those are the definitions. He does have a section on Fourier series and partial differential equations in here. So I'll go through that in here, but I'm going to have a whole, I'm going to do a whole class on partial differential equations later on. Okay, and here's some examples of differential equations. He starts out by, sort of like where all of this stuff began with Newton's second law, F equals ma. I'm sure everyone's probably familiar with this from high school, or I think it's fair enough to say that in modern society, most people are familiar with Newton's laws of motion. Maybe not. I don't know. I don't know. I think it is, though. Anyway, the velocity is the change in position over time, and acceleration is the change of velocity with respect to time, or you can think of it as the second derivative of position with respect to time. And with these definitions, you can write Newton's second law in terms of a differential equation. So F equals ma is m times the second derivative of y with respect to t equals m times g, where g is the acceleration due to gravity near the surface of the Earth. Here, notice that you can divide out by m, and that gives you this equation here. So the second derivative of position with respect to time is equal to the acceleration of gravity near the surface of the Earth. So this value g is approximately constant, as long as you stick close to the surface of the Earth. Right? In other words, this constant, this is telling us that gravity pulls us down to the ground, right? Here's some more examples, but actually, before I show you these and talk about these, I forgot to add this into that where he was talking about Newton's law, but you can that first version of Newton's law doesn't take into account other forces, for example, air resistance, etc. You can get a slightly more complicated looking second order differential equation here if you do take into account some first order properties of air resistance. So you get this linear term here, a first order term rather, due to air resistance. Right, so this is still a second order partial differential equation because the highest derivative that occurs is the second derivative. Right? And he has some other examples of differential equations up here. Some of them are famous. So here, these are some examples of some first order differential equations. Notice this is first order because the highest order derivative that occurs is the first derivative. Same thing here, the highest order derivative that occurs is the first derivative. And then next to it, we have some examples of second order differential equations, and that's because they involve the highest order of, the derivative is 2, right? So second derivatives. Those are second order. And then he also gives some examples of some famous, very important differential equations right below it. These are both second order because they involve second derivatives. This is called Legendre's equation, and the second equation is called Bessel's equation. So these are very important equations that come up in physics. I'm sure we'll be looking at these a lot in the book later on. If you've heard of Bessel functions, they come from this Bessel's differential equation. Right, we talked about that. And then he gives some important PDEs too, which we'll look at, I'm sure, in ad nauseum when we get to a PDEs class. So the first one is called Laplace's equation. Notice these are now all partial derivatives rather than ordinary derivatives. So if you take the sum of the three partial spatial derivatives and set it equal to 0, that's called Laplace's equation. The second one is called the heat equation, which is what led to Fourier series. And then the wave equation 2, which is another classically famous partial differential equation. Okay. And then so that's basically 1.1. He just, it's just like a introduction to what differential equations are. Then 1.2 starts here, where he gives the form of a general nth order ordinary differential equation. So an ordinary differential equation of the nth order is some function of these n plus 2 variables. So x, y, the first derivative of y with respect to x, second derivative of y with respect to x, and so on all the way up to the nth derivative of y with respect to x equals 0. Right, so that's the general form of an nth order ODE. Okay, and then he talks about how would you, given a solution, how would you verify that it is a solution to an ODE? And you do it in the ordinary way that you would verify any solution to an equation. Is you compute here, because it involves derivatives, you would compute the derivatives of the solution and plug it into the ODE and show that you get an identity. Okay, we'll do some, when I get to the exercises, I think I do one or two of those types of things. So you'll see how that works. Okay. Here's some difficulties that come up with differential equations. Sometimes when you find the solution, it's actually not possible to solve explicitly for the dependent variable in terms of the independent variable in the ODE. So for example, if you try to solve this differential, if you solve this differential equation, you get this solution. But notice that you can't actually solve for y explicitly in terms of x in this formula that we have here. Right, so sometimes that actually, in fact, a lot of times that actually happens. So. All right, another note, solutions involve one or more arbitrary constants equal in number to the order of the ODE. If you remember back to your days of calculus when you learned about integration, remember when you integrate, you get an arbitrary constant, right? The indefinite integral is a family of curves, right? It's the all antiderivatives that differ by a constant, right? Here's an example of the simplest ODE, dy dx equals some function of x. You can solve that just by simple integration. Y is the integral of f of x dx plus your arbitrary constant. The integral here may not be expressible in terms of a finite number of elementary functions. Again, this is something, if you've taken calculus before, that you should be familiar with. For example, this is a very famous function that you can't solve for in terms of elementary functions. We'll be looking at this when I get to a course on statistics and probability theory whenever that happens. This is also another famous integral, sine x over x. Both of these, if you remember back to your calculus, your single variable calculus days, you can't solve for these explicitly in terms of a finite number of elementary functions, but you can express the integrals in terms of power series. I won't go into that now, but whoops. Oh, and then here I'm just reminding you that the indefinite, this is called an indefinite integral, if you remember back to calculus. Right, it's a family of curves of all functions that differentiate to give you the integrand here, right? If you remember, they all differ by a constant. And then right below it, I have an example of an antiderivative. Right, so if you put in some limits of integration here, where the upper bound you leave variable, then this is a specific antiderivative. Okay, so in other words, if you differentiate this function, you'll get little f of x. Right, so this is a specific antiderivative. This is the family of antiderivatives. Okay. Okay, here's a definition. We just talked about how this thing over here is the simplest kind of ODE that you can have, right? It's just an integral problem. The next simplest type of ODE that you can have is a separable equation, which looks something like this. So a separable differential equation has the derivative of the dependent variable with respect to the independent variable. It can be expressed as a product of pure functions of the dependent and the independent variable. All right, and then you could solve this by separating variables, and then you can integrate both sides and solve the differential equation. Of course, that's easier said than done, but these separating the variables is not difficult. Okay, so here it's just another note about the difficulty and some of the difficulties inherent in the subject of differential equations. This is what the general first order equation looks like, right? It's some function of the independent variable, the dependent variable, and the derivative of the dependent variable with respect to the independent variable equals 0, right? So that's the general first order equation. We would think that this equation should have first of all, there should be a solution to it, and the solution should contain one arbitrary constant based on what we just said about integration and everything, right? But here are some examples that sort of throw a wrench in the works. If you look at this first order differential equation, if you take the square of the first derivative of y with respect to x plus 1, this has no real solutions. So no real solutions at all. Okay. And the one below it, if you have the square of the first derivative of y with respect to x plus y squared equals 0, this only has a single solution and no arbitrary constant works. So, sorry, I should say no non-zero constant works. So this leads to questions of existence and the nature of solutions of differential equations, and that we have a theorem that tells us about that. Well, let me show you that theorem first, and then I'll get to the intuitive notion. So here, Picard's theorem is a statement about that type of thing. He doesn't prove this early on in the book. He proves it in chapter 13, and it's a very difficult statement to prove. So we'll have to wait for a while to get to the proof of this. So if fxy and partial f partial y are continuous functions on a closed rectangle R, then through each point x0, y0 in the interior of the rectangle, there passes a unique integral curve of the equation dy dx equals fxy. Okay, that's Picard's theorem. It tells us, this it tells us that for a fixed x0, the integral curve is completely determined by the y value of the y value of the original point, y0, or the initial, the initial point. Integral curves are one parameter family of curves. So in other words, because this C is arbitrary, you get a family of curves as the general solution, where different values of C give different curves in the family. And given an initial point, given an initial point x0, y0, the corresponding value of C that makes the general curve pass through that point is solved by solving this equation. So if you solve this equation for C, you'll find what that value has to be. So this is analogous to finding like a specific antiderivative rather than the indefinite integral, right? So you have the general solution looks like this, and the particular solution satisfying the initial conditions x equals x0, y equals y0 looks like this. Notice we have a specific value plugged in for C0. This is the unique value of C0 that makes the integral curve pass through this initial point. All right. So like I said, we'll actually get to Picard's theorem. I think he said in chapter 13. But let me go back real quick. This is basically the end of the notes, except for that one part that I skipped over, where he just gives a little bit of intuition about, what the differential equation tells you. So if you assume that dy dx is fxy, assume that it can be solved, and f is continuous on some rectangle in the xy plane. If P0 is some point x0, y0 in the rectangle, then if you evaluate the derivative of y with respect to x at that point, you get this number here. It just comes from the differential equation, right? This geometrically determines the direction that the integral curve should be headed at that initial point P0. So in other words, if I go down here at P0, so the curve might look something like that, right? At P0, the derivative is telling you the tangent line at that point, right? The direction that the curve is headed. So it gives you a direction to go at P0 that sort of follows the curve, if that makes sense. And if you pick another point that's close to P0 that lies along that direction, then you can find the tangent line at that point that gives you another direction. And again, you can choose another point along that direction, find the value of the differential equation there. That gives you another direction. And so you get sort of like a piecewise approximation to the continuous curve. And as the points get closer and closer together, the broken line becomes the actual continuous integral curve that solves the differential equation with this initial condition, right, P0. And in general, different initial points will give you different solution curves. Okay. So that's essentially what he talks about in section 1.1 and 1.2. It's a relatively short introduction. So I'm going to end this video here, and actually when I end this video, I'm going to do the next video where I talk about the exercises and the solutions that I did for those exercises. I'm going to do that right after this one. So I'll see you guys in that video. I think the next video I'll post after these two on the Simmons book. The next one I'm going to post is on the lecture notes for the chapter notes for section 1.1, 1.2, in the John Taylor book, the classical mechanics book, and then I'll swing back around to do the exercises for Schifrin's section 1.2 in his multi-variable mathematics book. All right, so I'll see you guys in that. See you guys then. So I got a bunch of videos coming up this weekend, so keep an eye out for those. And let me know what you think in the comments. And also, if you like this kind of content, let me just stop the screen share for a second. If you want to see more of this content, please do me a favor and like and subscribe so that YouTube will, know to share this with people, and other people that have the same interests as you and I can enjoy them. And I guess that's it for this video. So I'll see you guys in the next one.